All right, guys, this is lecture 2 for chapter 8. We're going to go through the 3 hydration reactions. So in this lecture, we're going to be covering, let's make sure we have a pen. There we go. Reactions that add water across a double bond. All right, so you're going to add OH to one side and H to another. Why are we going to do 3 different reactions? We're going to do acid catalyzed hydration, and that is going to be a Markovnikov reaction, but this one will have rearrangements or potential for rearrangements. We will do oxymercuration, demercuration, and that is also Markovnikov, but no rearrangements. All right, so you have 2 options there. Now, why would you want one that could rearrange when you have one that couldn't rearrange? Well, there's always issues with the expense of materials, how important that step is for you, right? We love to have options. We love to have tools in our organic toolbox. And then finally, because we are the control freaks that we are, we're going to have hydroboration oxidation. Hydroboration oxidation will give us our option for an anti-mark, right? Anti-Markovnikov. So we will have control over that regiochemistry. This one doesn't have any rearrangements either. No, ooh. Well, that should say rearrangements. Here we go. Okay, acid catalyzed hydration. As you can see, it's going to start with an alkene. This is a chapter all about adding 2 double bonds. And now we're using H3O+. We're using dilute acid. That's the point. So if we are going to see this on an exam or a quiz, there's a couple ways that you might encounter this, right? H3O+, water, and H2SO4. Often sulfuric acid is the acid of choice. You may also just see it generically written as H+ and H2O. What's important here is that you are getting a dilute acid, right? And we're going to add that OH to the more substituted side. And of course, let's see, there were 2 hydrogens on that double bond, on that carbon at the end, and now there are 3, right? Because we added water across the double bond, right? The OH and the H. Let's look at the mechanism of this reaction. I'm going to use 1-propene. Now, the rate is affected by the type of alcohol. You've got primary, secondary, and tertiary, but you get the same product. You still add water across the double bond. Let's think about why tertiary might be so much faster. This is going to be explained in our mechanism. The first step should look familiar from the last lecture that we had. You are going to go ahead and have your alkene act as a base. It's going to pick up a proton. The hydrogen is going to go to the side with more hydrogen because that leads to a more stable carbocation. Right? So the hydrogen went to the end. We wound up with a secondary carbocation. That's why something like something with more substitution reacts more quickly, because in this case you would get a primary carbocation, secondary, tertiary, right? The more substituted that carbocation is, the more stable. The more stable the intermediate, the lower the activation energy. From here, water is going to act as our nucleophile, right? There is no hydroxide, so you should not be drawing hydroxide. The water will add, right? We're going to attack that electrophilic site. We can't just lose atoms willy-nilly, so we do have one last step. This is acid catalyzed hydration, So that should indicate to you that we get the acid back. Now, what's going to take that proton? Well, water. Water is acting as our base as well. You could show the conjugate base of whatever acid, right? HSO4 minus, but it's most appropriate to use water. That's typically what you're going to see here. And so that will leave us, right? Those electrons stay with the oxygen. That will leave us with our alcohol product. You have that stepped out through your slides. It's a proton transfer, nucleophilic attack, followed by a proton transfer. All of these are reversible steps because this is simply the reverse reaction of what we saw with acid catalyzed dehydration in chapter 7, where we use concentrated H2SO4. With Le Chatelier's principle, if a dehydration gives you water, we add more water, that's going to push the equilibrium in the other direction. So for acid catalyzed hydration, we just need to add water. Now, anytime you have anytime that you have a carbocation, so let's say we have this guy here, H+, you will have the possibility of a rearrangement, right? So you might see water adding in ways that you weren't expecting. Here we go. There's 2 steps to that last part. Because the carbocation would undergo a hydride shift to go from a secondary carbocation to a tertiary carbocation. When it comes to, so regiochemistry could be affected by that. Stereochemistry, as you see on this slide, is not going to be super interesting. Well, maybe that's the wrong way to say it. It's going to be a mixture. So if you do create a chiral center, because that carbocation is flat, you could add the water to the front or to the back side of that, and you are going to get racemization. You're going to get a racemic mixture of the 2 possible enantiomers. So oftentimes you just won't see me draw the wedges or the dashes. All right, how can we address this rearrangement? Oxymercuration, demercuration. We're going to look at part of the mechanism, but on these next 2 reactions, you will not be responsible for the mechanism. So let's say that one more time. In this set of reactions, you should be responsible for the mechanism for acid catalyzed hydration, but you will not have to know the mechanism, or you will not have to be able to draw the mechanism for oxymercuration, demercuration, or hydroboration oxidation. All right, it's a Markovnikov reaction, but no rearrangements. So what we see here, and let's use this example from above, right? This is where you might actually see a rearrangement. This is a 2-step reaction, so it's important that you do a 1 and a 2. You cannot put all of the reagents in one pot. You must separate them. The first step is to use mercury acetate. Mercury acetate looks like this. You have a mercury atom, and then an acetate, which is mercury OCOCH3, and then you have the same thing on the other side, if you wanted to know what that looked like. That's mercury acetate. Now, mercury acetate falls apart on its own, so you get this mercuric cation. You also need water in that first step. The mercuric cation, what's interesting about that is when you attack the ion, instead of picking up a proton, you actually form this mercurinium ion right here. This mercurinium ion, this 3-membered ring, is the reason you don't get rearrangements, because you are occupying both carbons there. The second step is going to require you to use something called sodium borohydride. Sodium borohydride finishes off this reaction. In step 2, we'll come back to that. It when you have that mercurinium ion, your nucleophile, in this case we're using water, is going to attack. Now it's going to attack the more substituted side because as this bond forms and this bond breaks, you notice you have a partial positive. Well, where is that positive going to be the most stable? But it's going to be the more substituted carbon. So it's the same reason a carbocation forms on that more substituted position. That opens up that mercurinium three-membered ring. And it's still, so you still wind up with the water on the more substituted position. Let's adjust this. But you wind up with the mercury acetate on the less substituted position. The second step, which you really don't need to understand the mechanism for, just finishes off the reaction. The sodium borohydride kicks off the mercury acetate and goes ahead and reduces that OH to, where you added the water, reduces it to just an OH. So that's the last step. So the takeaways are you need to know these reagents. You need to know that it is a 1 and a 2 step, and that it is going to give you a Markovnikov addition of water. So the OH to the more substituted side, H to the less substituted side. Again, you don't need to know the mechanism on this one. So from here, we're going to jump into this last reaction we're talking about today, Hydroboration Oxidation. So if we want to add our OH to the less substituted side, anti-mark, we are going to use a different two-step reaction. We're going to use a boron reagent. Now, what's most important to recognize here is it's boron. You might see BH3, you might see BH3 THF. THF is a solvent that helps stabilize this. You might see B2H6. Later on, you may see an R group involved. What I want you to focus on there is that boron. You're not going to see boron in any other types of reactions. The second step is going to be the oxidation, and it's going to use peroxides. I like to note that because peroxides were also involved in the anti-mark addition of HBr. So I tend to think of peroxides as being critical for that anti-mark addition. It's going to put the OH on the less substituted side. Now, you don't have to be prepared to give me this mechanism, but what I would like to show is why this works. So we're not going to, oh, yes we are, okay. The stereochemistry that you do need to be introduced to, you'll see on a lot of my practice problems, I like to use rings because rings are the most kind of easy to show the stereochemistry of addition. Either something can add both to one side where you get the OH and the H, both cis, either with wedges or with dashes. This would be a Syn addition. Syn means they're adding to the same side of the double bond. This is a Syn reaction. An anti-reaction means the two things that added would add trans, the OH on one side, the H on the other. This is going to be something that you have to predict when you're doing product predictions. So if we were to finish this off here, we've got our BH3 in step 1, our peroxide, and our sodium hydroxide in step 2. I did not give you an asymmetric double bond here. So it would just, all you'd really have to show me is that the H and the OH that added are on the same side. Here's a better example because you do have an asymmetric double bond with a methyl group. So the OH is anti-mark, so it's adding to the less substituted side, the hydrogen to the more substituted side. If the OH and H are on the same side, then the methyl is on the opposite side. Oops, sorry. Let's see. Now, the geometry of this is why this works. So you've got your borane, your BH3 with an empty p orbital. It does often form dimers and you get a B2H6. You can skip over that. This just shows you how THF can stabilize it. Again, you are not going to be responsible for any of these structures. The mechanism here, I only want to point it out because it helps me to understand why it is a Syn addition and why it's anti-Markovnikov. The double bond is going to donate electrons into that empty p orbital on the boron. But at the same time, that BH bond is going to be attracted to the carbon that's losing electrons. All right, so you wind up getting this four-membered kind of square-ish intermediate or transition state. You add the boron and the hydrogen at the same time. So since they're adding at the same time, it's going to approach the same side of the double bond. This bond here wouldn't be big enough for the boron to add to one side, the hydrogen to add to the other. So they add at the same time. The boron goes to the less substituted side, the hydrogen to the more substituted side. The very last step with the peroxide replaces that BH2 with your OH. That is definitely not covered in the mechanism, so you do not need to know that. So what do you need to know? You need to be able to predict the anti-mark product, and if stereochemistry is a factor, wouldn't be a factor on something like this. For me, when I ask you about the stereochemistry, it'll be in a ring format so that it's really easy. You're using wedges and dashes, right? The OH and the H should be on the same side. I'm sorry if that wasn't super clear here. Let's erase that. Make sure that it's very clear. The OH and the H are on the same side. All right, in the next, again, here's a picture of the overall mechanism of step 2. You absolutely do not need to know this mechanism. If you just really like mechanisms and are interested in it, well, get into it. We will not be interested in any sort of stereoselectivity except for what I've drawn here. On a ring, I want you to be able to show me that this is a Syn addition. We will not worry about chiral centers other than that. And so if we were just going to do a practice problem here, right, I got to go fast. Let's see. There's no reason that stereochemistry should change. So since this is a Syn addition, let's say, that came from the back side of the ring and push that methyl group forward, your hydrogen would be there, your OH would be at the less substituted position. Okay? There will be practice for this.